Olympiads. He won a silver and a gold medals in the IMO editions of 91 and 92, some time ago, right? And after the Olympiads, Patrick got his PhD title from the École Normale de Paris and spent some time in the Université de Valladolid and at the École Normale de Lyon. In 2002, he was hired as a maître de conférence at Université de Paris 7, and since 2010, he's a full professor, at Université Lille I. Patrick's main research interests are singularities in both algebraic and analytic geometry, and symplectic and contact topology, as well as toric and tropical geometry. Patrick has a real pleasure in communicating mathematical ideas. I invite you to take a look at his 60 contributions or so to the website Images de Mathématiques, and also to read his wonderful book, What is the Genius?, where he discusses history of this central concept in today's mathematics. So please join me in welcome Patrick PopescuPampu.
Is it better? So I start again. It's a great pleasure for me to be in such a wonderful place where a lot of great mathematics were developed, and which helps, in fact, I think, the whole world to see how every part of the world can develop mathematically with a great speed. Congratulations for what was realized till now in Brazil, and I hope that this has exponential growth. So I will speak today about a story trying to converge to a joint work with Maria Angelica Cueto, who works in the United States but is of Argentinian origin. She works in Columbus, Ohio, and Dmitry Stepanov from Moscow. It's a story about a tropical and logarithmic study of Milnor fibers. In fact, it's a story about singularities, isolated singularities of complex surfaces. Well, I will draw a surface. I'm obliged to do real drawings. And even when one experiments, I experiment a lot by drawing, one has to learn how to think in the complex world by doing real drawings. So let's start. I try to draw here a circle in perspective. So you see, I drew a surface of revolution. Let's try to draw some circles in order to help our eyes to imagine it. Also here. And this surface of revolution has a singular locus. It has here a whole circle of singularities. So these are non-isolated ones. And it has also two isolated singularities, here and here. I will concentrate on such singularities, and I won't look at all at such non-isolated singularities. Concentrating on isolated singularities means that one first wants to isolate a local piece from which all the global aspects of the picture had disappeared. So concretely, this means to choose a small ball around the point here. And in the ball, you see only something, a singularity which looks like a cone. So concretely, such a ball is called a Milnor ball. You see already appearing here Milnor, and the Milnor fibers will be objects which live in Milnor balls. My object suggests to you a surface in three-dimensional space. One can complexify it, arrive in three-dimensional complex space. In fact, I'm interested in singularities which live in any dimension. So you have to imagine that this object lives, for instance, in dimension 100. I'm not interested in the dimension of the ambient space. I'm interested in the fact that this is a surface. And one can do such constructions with Milnor balls in any dimension. So let's try to zoom on this, and let me make the picture like this. By taking the Milnor ball here, we will look at the intersection of our surface, which here goes farther, with this sphere. So symbolically, I draw a circle, but one has to think that because we work with complex surfaces, this is of real dimension 4. Therefore, this intersection here with the sphere is of dimension 3. The singularity being isolated, if the sphere is sufficiently small, a basic theorem is that it is transversal to the surface. Therefore, here this is a 3-dimensional manifold. And the complex surface being naturally oriented, well, you can imagine that it is as if this surface here was oriented, this orients its boundary. So in fact, this is naturally an oriented 3-manifold, which is called the link of the singularity. Singularity for me, I will repeat all the time, singularity, singularity. Singularity means like this, a germ of complex surface at an isolated singular point. So here, singularity means the germ of the surface X at this point. And one captures usually the topology of the germ in this 3-manifold. The germ is in fact topologically the cone on it. So a basic question is, what 3-manifold one obtains in this way? This is completely known since the 60s, and as many other questions about singularities, it is solved by resolving the singularity. What does it mean to resolve the singularity? It means to do a kind of surgery. Take out the singular point and replace it by something else such that the new surface becomes smooth. It turns out that one can do this by replacing the singular point by a curve whose irreducible components are smooth and intersect mutually in the simplest way, which is called normal crossing. I will do here another symbolic real picture. So one has a map like this, which can be seen as a kind of shade map. This is the map which is called resolution of singularities. And my point here is replaced with a configuration of curves, and I will draw 3 of them. 3 circles, but one has to think that these are complex curves, and a complex curve is a Riemann surface. So in fact, behind each curve, each circle here, one has to imagine a surface of some genus. And I finish with a third one. Let's draw it in this way. So you see that they are joined in this way. The first cuts the second, which cuts the third one. Why does this help to understand this 3-manifold? Now one can lift this 3-manifold above. A resolution, as I told you, means that one replaces this point by this configuration of curves. Now one is inside a smooth surface, and the part outside the singular point is identified with the part outside the curves here. So in fact, I am inside the surface, and this which could be seen as boundary of a neighborhood of this point lifts here to a boundary of a so-called tubular neighborhood of this configuration of curves. So let's draw it here. So a word about such a real picture. Here you have to imagine that these circles are inside a smooth surface. And then you have to ask yourself, I have a circle in a smooth surface. What is its tubular neighborhood? A basic fact about tubular neighborhoods is that they are fibered by transversal disks like this. So a tubular neighborhood here of a circle will have a structure of segment bundle, if I'm in the real case. And such bundles are of 2 types, either cylinders or Möbius bands. So when you do such a drawing, you have to ask yourself for each circle, do I have a cylindrical neighborhood or a Möbius band neighborhood? So here in my drawing, I will combine both, and I decide that here on the left I have a Möbius band neighborhood. That's why here I pass on the other side. And then I continue, and I chose to draw a situation where in the two other cases we have cylindrical neighborhoods. So here you see this torsion which creates the Möbius band. And that's it. And now you see that this three manifold, making it smaller and smaller and smaller, degenerated to a point, and to say that something degenerates to a point, well, teaches you absolutely nothing on the object. Here the things are different, because the three manifold degenerates to this configuration of curves, which has global structure. And this global structure allows you to understand in a second step the structure of the three manifold. How? Precisely by looking at this bundle structure here. So now we have to imagine that this is in the complex situation. So here we have small disks. And we have here this situation, you see absolutely everywhere excepted near these points where two curves intersect. So here there is a conflict between this fibration in this direction and the fibration in this direction. One has to understand what happens. Here it happens twice, near this point and near this point. So let's zoom and isolate this situation. I have this, and now I have here locally my three manifold, which comes like this. So it is, we have a fibration by disks here, a fibration by disks here, and what happens? Well, the key is to see here inside this square in the real situation. You see? And now, this vibration can propagate here, and this vibration can propagate in the transversal direction here. And in fact, they meet precisely here at the level of the boundary, at the level of the vertices of the square. And the same happens in the complex situation. But one has to understand what the vertices of the square mean in the complex situation. So let's look. Here the vertices of the square are in fact a Cartesian product of these 2 points here and these 2 points here. And these points are the boundary of this segment. But this segment, it's a complex situation, is a disk. So the boundary of the segment becomes a circle. So these 2 points represent a circle. These 2 other points represent a circle. The Cartesian product of 2 circles is a 2-dimensional torus. So these 4 together in the complex situation give a torus. And on this torus, you see that here you have disks. At the level of the boundaries of disks, you have circles here, which arrive on the torus. Well, from one side and from the other side, they arrive exactly in the standard way, like a circle here and another circle in this way. So you see the conflict. You cannot pass continuously from this circle to the other one. There is a brutal change of circle. Well, this is no problem. This means that here you will have a torus. Here you will have another torus. And if you cut the 3 manifold along those tori, in the pieces which remain, here we have 3 pieces, we have structures of circle bundles over some surfaces with some genus. Well, okay, this dictates that we have a manifold which is cut into pieces by 2-dimensional tori. Such a manifold, such that the complement of those tori, moreover, is fibrated by circles, is called a graph manifold. So we obtain the fact that M3 is a graph manifold. Why graph manifold? Because this structure can be completely encoded by a graph, by representing each curve here by a point. These are the vertices of the graph. 1 point, a second one, a third one. And now we join 2 points if the corresponding curves intersect. So we have to join these 2 and these 2. And now we have to say what is the structure of each curve. So here I made a real drawing. I told you that we have a complex situation. Well, they can be any genera. For instance, this here could be of genus 0. The one on the middle could be of genus 3. The one on the right of genus 1, which means that here we have a sphere, here a genus 3 surface, and on the right a torus. And moreover, one has to say how those curves lie in the ambient smooth surface. Topologically, this can also be encoded by one number, which is the self-intersection number of the curve in the surface. To understand this notion in the most intuitive way, you have to imagine that you move a little that surface differentiably till it cuts itself only in a finite number of points. And then you count those points with multiplicities. Not with multiplicities, sorry, this is an error. With sides. Because the surface is oriented. We are in an oriented four-manifold. When we move continuously, we keep the orientation, and then we look locally if putting the 2 orientations together, we have or not the ambient orientation. And here, what is miraculous is that if you resolve singularities, all those self-intersections are negative numbers. So for instance, it could be here -3, -1, -2. This is a general rule. They are not only negative numbers, but from this graph decorated like this, one can build an intersection form, which describes globally how all those curves intersect. That intersection form is negative definite. This is a fundamental result about the topology of singularities going back to Duval in 1945 and Mumford in his first work in 1961. In fact, it was Mumford who studied the links of singularities in this way and who understood that there are those tori which intersect the boundary. This story is then propagated in topology in the 60s through works of Waldhausen, who classified the graph manifolds. The classification problems comes from the fact that a same manifold can be given by different graphs, and he said, described precisely when 2 graphs give the same manifold. And then, in the 30s, developed the Jakob-Schall and Johansson theory of the structure of 3 manifolds, saying that indeed 3 manifolds should be cut into pieces by tori. There are the pieces which are fibered by circles like this. Okay, we understand them. And there were others which were mysterious. And there, Thurston came with his conjecture saying that the other pieces are hyperbolic, which was proved finally a lot by Thurston and his students and other topologists, and completely by Perelman. But you see, all this started with this work of Mumford in 61, studying the links of singularities. And I think it's very interesting to see how ideas propagate from one field to another. So let's come back here. I told you that these are negative. So you see, this says that if you want to move those curves, you are obliged to move them in the differentiable category. You cannot move them holomorphically, because 2 holomorphic curves, well, if they have only a finite number of intersection points, those points count positively. And if you count positive numbers, you addition them, you get positive numbers, not negative ones. So in fact, such curves appearing by resolutions cannot be moved. They are rigid in some sense. Okay, so let's come back here. So you see, these are the graph manifolds, which are determined by graphs. And in fact, boundaries, links of singularities, are exactly the graph manifolds which may be described by a graph whose intersection matrix is negative definite. So like this, I told you, we understand those links. Yes, we understand this in this way, with this negative definiteness condition. This is, in fact, a theorem which is obtained by combining work of Mumford in 1961 and of Grauert the same year. Okay. Now, let me give you the simplest example of such a resolution. A priori, it is difficult to know how to resolve, how to arrive and to see exactly what lies inside. But the simplest example of surface singularity is the quadratic cone. Okay? This quadratic cone is filled with lines. Passing through the origin. And in fact, if you projectivize it, which means that you look how it cuts the hyperplane at infinity, you get a conic. And you know that a conic, abstractly as a curve, is a curve of genus 0. Now, how can one resolve this singular point? Well, by replacing this point with abstractly this conic. It means why we have a singular point. You see that the lines individually are smooth. The singularity comes from the fact that those smooth lines intersect. All of them pass through the same point. So in order to resolve the singularity, we will separate the lines. On the real things, you can imagine that you do this by constructing a cylinder. The cylinder is also filled with lines, but which are parallel, like this. Let me put a third one here. And now the point here can be seen as an image of a meridian circle on the cylinder. Again, one has to understand the complex situation. Over the real, this is correct. But you see that over the reals, this circle can be moved by translating it parallelly with itself, and then it won't intersect itself. It seems like the self-intersection is a 0. Which contradicts what I told you here, that it should be negative. But this is only a real phenomenon. You have to know, as I told you, that a curve in the real world has only 2 types of neighborhoods. So in fact, it has only 2 types of self-intersections, 0 and 1. But those 0 and 1 have to be computed modulo 2. And those numbers, parity, are in fact the reduction modulo 2 of the self-intersection over the complex numbers. So doing these drawings is not something which is completely free. It's very important to respect the parities of what happens over the complex numbers. So you see, moreover, here that this local situation is like the local situation here in the drawing I did before of the global surface. And the symbolical one I did just before looks more like the one here. And over the reals, here you see the difference. That in this case, the real link is 1 circle, and here the real link is 2 circles. So here you see a difference on the real topology. And here there is a trick. I was obliged to make a Möbius band here in this drawing, because otherwise I wouldn't have had a boundary which is connected. And I wanted here to draw a resolution of singularities of this one, not of this one. So one has to be careful about these parities. And this is a pleasure of doing such drawings. So I repeat this because nowadays it's not very fanciful to teach to students to draw. I teach them a lot to draw because it's a great experimental tool. So let's come back here. In fact, over the complex numbers, one has to think a little more. One sees that the self-intersection here is -2. In fact, this -2 is the opposite of 2. And what is 2? 2 is a degree of a conic. So in fact, by looking at what happens at infinity, you see I have a conic. A conic abstractly is a sphere. So in fact, here, you see I have only one curve. The graph is reduced to 1 point. Knowing that it is a sphere, it has genus 0. And I put here -2. And this -2 is the opposite of the degree of the conic. So this happens always for cones over plane projective curves. You know to resolve them in this way by separating the generating lines. And the self-intersection is the opposite of the degree. The curve will be this one of genus. Well, the genus of the corresponding curve, and there is a formula known since the 19th century. A smooth curve of degree d in the projective plane has genus 1 plus d minus 1, d minus 2 over 2. So you see, in that case, you know how to resolve. Okay. This is a very nice example also because now you know that the link is three-manifold, graph three-manifold, which has this encoding, but it turns out that it is also the real projective space. And it has also a description as the cotangent bundle of the unit cotangent bundles. In a cotangent bundle, you take only vectors of norm 1. The cotangent bundle of the sphere. And in fact, by working on this, you can find each description. And it's very interesting to see those descriptions. It's worthwhile spending time on these examples. How to see these other things? Well, there one has to play with an equation. So, for instance, x squared plus y squared minus z squared equals 0. And one has to complexify it. So a trick, if you want to find the second one, unit cotangent bundle, you have rather to put here a plus than a minus. The minus, I put it in order to get the correct real situation I showed you before. And now you write real parts and imaginary parts. You break this into two equations, and you will see popping out the unit cotangent bundle. Okay. And this last description is also interesting, because you see the unit cotangent bundle is naturally the boundary of the disk cotangent bundle. And it turns out that the disk cotangent bundle appears naturally in this situation. How? Well, you see that a quadratic cone is a limit of a smooth quadric. The outside quadrics here are hyperboloids with one sheet. And you have also internal ones here with two sheets. Again, they are different over the reals, but if you take their complex points, they are the same. And this comes from what? When we took these different surfaces here, in fact, we took level lines of our function. So let's call it f is equal to x squared plus y squared minus z squared. This function is defined here in R3 with values in R. The real numbers are aligned here, but remember we have to imagine what happens over the complex ones. So the line has to be put in a plane. And here, these two different surfaces, the blue one and the green one, came from the fact that you look at a level to the right here and a level to the left of the origin. And the quadratic point corresponds to the origin. And why is it possible to expect a change? Because over the reals, when you cross a singular point, in general, you have a change of morphology. And in fact, singularity theory is the study of changes of morphology. So the prototype is this. Changes of morphology when parameters vary. So this is the simplest example. But over the complex ones, you see that these 2 points can be connected here in a circle. But now over each point of the circle, one has to put also the complex points. And in fact, when you complexify both things, well, you arrive at the same thing. And you don't only arrive at the same thing, but above each point here, you have always the same four manifold, real four manifold. All those things form, in fact, a fibration over the circle, a locally trivial fiber bundle. This was a theorem of Milnor, and the fibers of this fiber bundle are called Milnor fibers. So those are the Milnor fibers in my title. So you see, what I drew here, the two hyperboloids, are Milnor fibers, but only real points of Milnor fibers. And I am interested, more generally, in the structure of Milnor fibers. Those Milnor fibers are, in fact, four-dimensional manifolds whose boundaries are diffeomorphic with the link of the singularity. Why? Because the singularity was isolated. And in order to get boundaries, again, I have to cut here with a Milnor ball. And by transversality, things don't change by small perturbation. So I can say that the Milnor fiber, which is a four-dimensional manifold, has a boundary which is the link of the singularity. And in the SQL, I will always call the link M and the Milnor fiber F. So this is the Milnor fiber. And one can look at the most general question here: which four manifolds appear as Milnor fibers? Which four manifolds with boundary are Milnor fibers? This is a widely open question. There are not even conjectures about this. What is known, coming from the fact that there are complex surfaces inside balls whose boundaries are convex, is that they are Stein manifolds. If you don't know what it means, well, it is this. It's a possible definition. And the Stein manifolds like this of complex dimension 2, in fact, retract by deformation on a skeleton inside, which is a two-dimensional cell complex, which means that homotopically they are in fact of real dimension 2. Well, it means that those four manifolds are like this. But then inside the Stein manifolds, to find the ones which correspond to Milnor fibers, great theme of research. One needs a lot of ideas for conjecturing things. The only thing one knows, well, what are their boundaries? But there is then a big problem to know how to fill those boundaries in those four manifolds. So for the moment, I told you that it's extremely important to have conjectures. Happily, there are a few conjectures about them, but for restricted classes of singularities. I will show you one now. This restricted class is restricted topologically. It means that one asks something about the link. Namely, one asks it to be an integral homology sphere. So what is an integral homology sphere, which I will abbreviate ZHS, is a three-manifold. I won't use M. Let's put N, N3. I reserve M to the link of the singularity, is an N3 whose homology with integral coefficients is isomorphic to the homology of the three-dimensional sphere. It means that if you compute the homology, you won't see a difference with the sphere. This is an integral homology sphere. This means concretely the following thing. If you are not accustomed to work with homology, concretely homology speaks about being or not being a boundary. To be or not to be a boundary. This is the motto of homology and cohomology. So, being an integral homology sphere in dimension 3 means exactly the following thing, that each time you put a curve inside your manifold, it will bound, in fact, a surface of some genus. This is not important. In general, this is not true. There are curves in three manifolds which are not boundaries of surfaces. This means that the homology is non-trivial. Okay. So, the conjecture is the following. It was formulated by Neumann and Wall in 1990. At that moment, had appeared a new invariant of three manifolds of integral homology spheres. That's why there is this restriction, which was called the Casson invariant. I won't define it. It's difficult to define it in a few minutes. It would be a separate talk. But let's write Casson of the three manifold. And they conjectured that this is related to the Milnor fiber, that it is exactly 1/8 of the signature of the Milnor fiber. Here the signature means that one looks in the Milnor fiber at all possible surfaces inside, and one looks how they intersect. And one gets there an intersection form, and if you look at it over the reals, you have Sylvester's theorem, which tells that it's a sum and difference of squares, and you count how many positive ones you have, how many negative ones, you make the difference, that's the signature. But in any case, you see it's something about the topology of the Milnor fiber. So the conjecture is that if X, there is also an analytic constraint here, is an isolated complete intersection singularity. I will explain this in 1 second, in 20 seconds what it is. And M is an integral homology sphere, then one has this. This conjecture is still open, and I think that mainly it lacks strategy. This is still very mysterious. One does not have an idea of why it should be true. But they proved it in many examples. Yeah, it is true in many examples. So what is an isolated complete intersection? Well, I showed you here one example of a surface in C3 defined by one equation. But now imagine that you go in C4 and you take two equations. So you take two functions from C4 to C2. It may be seen as a couple. And you look f equal g equal 0. What can happen is that, for instance, f equals 0 and g equals 0, which here are 2-3 manifolds, possibly reducible, share common components. So f equal g equals 0 can contain components of dimension 3. It won't be a surface. Each time you add a function, you will drop the dimension by at most 1. This means to be a complete intersection. That really with each imposition of constraint, you drop strictly the dimension. So this means isolated complete intersection, a complete intersection which is moreover isolated, and they put this constraint. In fact, it was not clear why should one impose this. There were games playing with this conjecture in a more general situation of Gorenstein. I won't define them, but so-called Gorenstein singularities. Several of you know what it means. There it is false. So it's not clear what would be the frontier. It's clear that it's true for some singularities, not true for others. Here one needs to understand better the phenomenon. So let me show the simplest example of surface singularity whose boundary is an integral homology sphere. This one was not. I told you that the boundary here is a real projective space. In projective space, you have lines. And you know from the time of Euclid that a line intersects a plane transversely in one point. Well, this says that the homology modulo 2 is non-trivial. And if the homology modulo 2 is non-trivial, this says that over Z is non-trivial. So RP3 is not an integral homology sphere. So let me show you one. Instead of putting here 2, 2, 2, you will put 2, 3, 5. X2 plus y cubed plus Z5 equals 0. Look at this surface and look at its germ at the origin. Well, in this case, theorem, it is an integral homology sphere. It's link. And it is the first one which was introduced by Poincaré in his last complement to analysis citus in 1905. Its link here is the Poincaré homology sphere. But this is not at all trivial. Poincaré defined it in a completely different way, using a so-called Haggard diagram, where you didn't know it was impossible to see 2, 3, and 5. So how to prove this? This came from a very important discovery by Seifert. In 1934, he introduced Seifert fibrations before Whitney introduced general fiber bundles. And what's very interesting, Seifert fibrations, the word fibration was introduced by Seifert, and they were not locally trivial. So as always, when you see objects appearing for the same time, I know many examples appear objects with singularities. It's very interesting that people see that they have to introduce new objects when they have problems with singularities. Here you will see the same. So what happened? If you look here, the difference between this and our quadratic cone here is that here one had a polynomial of degree 2, which is homogeneous. Here, well, it is not homogeneous, but it is quasi-homogeneous. By putting weights to the variables, one gets monomials of the same degree. And this can be done like this by looking at an action of C star on C cube of x, y, z. T multiplies x, y, z as t to the power. In front of each variable, you put the product of the two other exponents. 3 times 5x, 2 times 5, y, and t to the power 2 times 3z. Now, if you look at the link as the intersection of this surface with a round sphere is not invariant by this multiplication. But if you look at the circle of unit complex numbers, that leaves both the surface and the sphere invariant. So it will act on the link. And it will act without fixed points, because this action here has only one fixed point, which is the origin. So here all the orbits are circles. And then Seifert looked at the space of orbits. Not in this example. These were examples behind his mind. But he introduced topologically in general a 3-manifold and a projection coming from such a filling by circles. And here what you get is a base which is of dimension 2. And in this precise example, this base of dimension 2 is a sphere. And it has 3 special points representing 3 special orbits, which are simply the intersections here with the planes of coordinates. X equals 0, y equals 0, z equals 0. You can look, and those are special. In which sense? That if you look at one of those orbits, the nearby ones won't close at the same time. In terms of foliations, you have a non-trivial holonomy, and it will turn around several times before closing, and the number of turns is exactly the exponent you have here. So those numbers 2, 3, 5 can be seen as invariants of those orbits in their neighborhoods, so you can put them, attach them to the 3 points in the base, 2, 3, 5. So this is the base of the Seifert fibration, and this is a Seifert fibration. So what is a Seifert fibered manifold? It is a manifold foliated by circles such that you have a finite number of special fibers around which you have non-trivial holonomy. That non-trivial holonomy has to be encoded, in fact, not only by an integer, but by rational numbers, a rational number in general, except here in the situation of integral homology spheres, because Seifert proved the following. That the Seifert fibered, he did not formulate things like this. He did not see things for a fibered like me. He said differently. Seifert fibered integral homology spheres have a base which is like this. You have, the base is always a sphere. And now here the numbers of turns are P1, P2, P3, till Pn. And all those are pairwise coprime. GCD of Pi, Pj is equal to 1 for any I different from j. So it's not important that there are prime here. What's important is that they are coprime. And moreover, if you fix some numbers, there is a unique Seifert fibered manifold, which is an integral homology sphere, which is like this. And there exists a unique such manifold. Which means that when you give a list of coprime numbers, you get automatically a 3-manifold. Let's call it sigma of P1, Pn. The first example being this one, where we saw that this is sigma of 2, 3, 5. So you see that in the simplest non-trivial case here, we got the integral, the Poincaré homology sphere. Well, one can ask again, for all the other ones, are they also links of singularities? The answer is yes. But this was proved much later by Neumann in 77. That sigma of P1, Pn is the link of a concretely given singularity, a complete intersection given by a concrete system. The game is like this. Here you saw that the numbers should be put as exponents. Here we do the same. We put z1 to the power p1 plus z2 to the power p2 plus zn to the power pn equals 0. But this gives a hypersurface. I want to define a surface. So I have to add equations. The game is to add equations of the same type, again and again, with the same exponents. But one has to vary the coefficients here in front. So one has to choose a matrix of coefficients, and the rule is that the maximal minors have to be non-zero. This is necessary and sufficient to have an isolated complete intersection. And then the link will be this one. So these are famous equations. For one equation, it defines a so-called Pham-Briscorn hypersurface singularity. Here we have a Pham-Briscorn complete intersection. And this condition on coefficients was found by Ham, a student of Briscorn, at the beginning of the 70s. So here the names attached with this are Briscorn, Pham, Ham. Complete intersection. So great. So till now we saw several integral homology spheres. We can ask, are there other integral homology spheres? Yes. And this is in fact a very old operation which was introduced by Den in 1907 and named by Ziebenmann in 79. You can do the following. Start from two integral homology spheres and choose a knot in each one of them. Here I will draw a trivial knot, and here I will draw a non-trivial one. And then you do the following. Remove tubular neighborhoods of those two knots. Like this. Those are tubes. When you remove them, you construct boundaries, which are tori. You have two tori on each side. On those tori, you have a preferred curve, which is called a meridian here, which turns once around the knot, which bounded a disk inside the removed field torus. But there is also a preferred curve here. It turns out that because it's an integral homology sphere, there is, up to isotropy, a unique longitude here, which bounds in the exterior. It will bound a surface. For such a trivial circle in three-dimensional space, you see that this is exactly a longitude because it bounds a disk like this. But this is true. In integral homology spheres, you always have preferred meridians and longitudes. And the rule is to identify those two tori by switching the roles of meridians. If this is a manifold MA and this is MB, you identify MA with LB and LA with MB. And this was called splicing by Ziebenmann. And then the development of topology shows that in this way, if you play with the type of knots you use, you get an infinite number of different integral homology spheres. So in fact, the world of integral homology spheres contains inside it the world of knots in integral homology spheres, because you can do this and iterate, and you can put links here, and you get, in fact, something absolutely terrifying. The world of integral homology spheres is a very rich topological world. But Ziebenmann in 1979 concentrated on this construction performed with the previous ones, these sigma P1, P1, which are Seifert fibered. And he performed this. Let me take an example. let's take two integral homology spheres, each time with 3 special fibers. Here the numbers being 7, 2, 3. Sorry, I have to put the point here. And 11, 2, 5. I will continue this example. That's why I choose precise numbers. Each point here represents a fiber. So choose those fibers, this one and this one, as knots into these integral homology spheres. Removing those tubular neighborhoods is as removing the preimage of those disks. And then glue with this rule. You get an integral homology sphere, which is a graph manifold, because you see, cutting it along a torus, it will be filled by circles. Okay? So, Ziebenmann had the idea to encode this graphically in the following way. Represent these two by star-shaped graphs. And put the numbers on the edges here. 2, 3, 7. And here 11, 2, 5. And now indicate with arrows the fact that you chose those knots, and this gluing will lead to, in fact, an identification of these two arrows, and you get a graph which is not star-shaped, which is like this. 11, 5, 2. Well, this he called a splice diagram. And he showed that integral homology spheres, which are moreover graph manifolds, are always describable by such splice diagrams. And now appears a difference with links of singularities. If you ask which ones are links of singularities, well, you have constraints. Constraints coming from the fact that the intersection form of a resolution of singularity has to be negative definite. And this was expressed in terms of splice diagrams by Eisenbad and Neumann in 1985. They describe the precise condition, which is the following one. For each internal edge, as the one here, you make the products of the numbers on the edge, 7 times 11, and you subtract the products of the nearby weights here, 2 times 3 times 2 times 5. And in our example, it is 77 minus 60, and this is positive. And this tells me that this comes from a singularity. So this is a rule of Eisenbad and Neumann. So one knows that this is realizable as a link of a normal surface singularity. But in general, one knows nothing about it. In which dimension can it be realized? Could it be a complete intersection? This is still open. It's not known inside those realizable which ones are complete intersections. But in 2002, 2003, Neumann and Wall discovered that with a new constraint, in addition to this one could write an analog of this system. This constraint is the following. I show you in the same example here. The rule is like this. You attach a variable to each leaf. Z1, Z2, Z3, Z4. Exactly like here, I told you that, sorry, my Poincaré homology sphere disappeared. So just remember, I told you that the 3 special fibers corresponding to the intersections with the planes of coordinates. So you had a bijection between the special fibers and the coordinates. In the same way here, there are special knots represented by the leaves of the tree, and they will correspond with intersections with the hyperplanes of those coordinates. So now the game starts like this, and we do the following. Here, you saw that we have systems of equations where what was important is to choose the exponents. Well, we go here. This surface will be defined in C4 with 2 equations. One equation will correspond to this vertex, the second one with this vertex. Let's go to the left here. we will have, first, you see an edge going directly to a leaf. That's simple. We will put Z1 to the power 2 plus a second one going to a leaf, Z2 to the power 3 plus, and this one goes to two other leaves. Here one has to build a monomial in these two variables, Z3, Z4. So one has to choose here two numbers. The rule is the following. In this direction you see here the number 7. So with this number 7, from here to here you will go to the two final leaves on a geodesic, to Z3. And you look at the hairs getting out of the geodesic. Here there is only one, on which you read 5. So you try to express 7 as something times 5, plus, and you do the same for the other one. Here you have on the hair 2, plus something times 2. It's possible. It's 1 times 5 plus 1 times 2 in the unique way. So that's why we put 1, 1 here. This concretely means that you try to see if a number belongs to the semi-group generated by 5 and 2. That's why they call this a semi-group condition. For other numbers, it won't be true, it won't belong to it. So you cannot write the equation, you are stuck. So you see, you are stuck in a game, but it's still not understood this game means what. We are in an experimental period around these problems. One has to invent new ways of writing equations. But here everything's okay. The second equation, well, you go to this point on the right. Again, to Z3 you will have here Z3 to the power 2 plus Z4 to the power 5, and you have to play the previous game in this direction where you see 11 here. So for 11 I write 11 equals something times 3 plus something times 2. So how can you write this? Well, for instance, here there are various solutions. All of them are correct. If you remove 3 from 11, you have 8, which is 4 times 2. You have 1 and 4. So you can put 1 here and 4. And their theorem is that this system has a link which is an integral homology sphere, which is a graph manifold with this splice diagram. Great. What do we earn by having a complete intersection? Is that a complete intersection has a Milnor fiber. You simply do the same game as with the Milnor initially. You take this system, and instead of putting equals 0, you put equals epsilon 1 equals epsilon 2 with small values, epsilon 1, epsilon 2. This defines a 4 manifold with the same boundary. So what 4 manifold is it? What they had in mind when they invented this, it was to be able to push their study of the Casson invariant conjecture. So they tried to see, well, now we have new examples of isolated complete intersections whose links are integral homology spheres. Let's see, is the Casson invariant conjecture true? The techniques were sufficiently developed to be able to compute the Casson invariant for this 3 manifold. The problem was the signature for the Milnor fiber. And they saw that the conjecture could be proved if one had a kind of analogous description for the Milnor fiber. They conjectured the following, Neumann-Wall in 2004. Well, that if you take the Milnor fiber of a singularity like this, given by a splice diagram, here I show one internal edge, any one, you choose the one you want. Here this extends, it has global structure. Then you cut here, and you get a left side and a right side. The conjecture said that this could be expressed by a 4-dimensional splicing procedure from the 2 Milnor fibers of the 2 resulting singularities. And they describe concretely what this means. If the conjecture is true, then the Casson invariant conjecture is also true for this class of singularities. In the meantime, Nemeti and Okuma proved in a completely different way the Casson invariant conjecture for these singularities without looking at the structure of the Milnor fiber. But the conjecture, this one, remained open. So I finally converged to the theorem done with my collaborators, with Cueto and Stepanov, is that the conjecture is true. The Milnor fiber conjecture is true. And I have only 2 more minutes. 1 minute for the tropical and 1 for the logarithmic study. It's terrifying. I'm very sorry, but you see it's difficult to describe both the context and the techniques. So, just their splicing operation is like this. The 3 manifold, I will represent it as here, and the Milnor fiber as a disk. So you have to imagine that this has internal structure. And here you have a knot, which is represented by this direction. And here you have a second one and a second knot. It turns out that there is a natural way to see this knot as the boundary of a surface embedded in this 4 manifold, and the same here. Now you can do the same game as in dimension 3. Remove a tubular neighborhood here. Remove a tubular neighborhood here. And on the level of the boundaries here, you had to identify the 2 tori in the rule I showed before. You could say, well, I will identify all these parts. But this is not possible because these 2 surfaces in general have completely different genera. They are not diffeomorphic. So the rule was to introduce a third piece, which is a Cartesian product of these 2 surfaces, this and this. And now here, on the boundaries, this part and this part, you see exactly these parts of the boundaries, which can be glued here. So you glue one complement here and the other complement here. And you see you get a new 4 manifold, and on its boundary, you see exactly the 3 manifold obtained by splicing here. So the conjecture is that the Milnor fiber of those singularities decomposes into 3 pieces, which are put in this way, a central one which is a Cartesian product, and 2 other ones which are Milnor fibers of 2 other singularities which are cut along certain surfaces. Why was this conjecture very interesting for us? Because there is, for the moment, no result of this kind, which expresses Milnor fibers of some singularities in terms of Milnor fibers of other singularities. We saw this as a beginning of molecular theory of Milnor fibers, to be able to build them like this successively and reducing to simpler singularities. So that's why we concentrated during several years on this. And what's tropical geometry? In this context, tropical geometry tells us how to modify, first, how to deform in an intelligent way this system by introducing special monomials, and then how to modify the total space in a way in which we will understand the special fiber. That is tropical. It's a game on exponents. You have to know that if you have a concrete system of equations and you have to play with it and the precise exponents are very important, there you need tropical geometry. And we started the project believing that tropical geometry is enough. And during the project, we saw that we have a lot of difficulties coming from the fact that if you want to understand Milnor fibers, in general, they will degenerate to something cut into many pieces like this. And if you want to understand classically by integrating vector fields, it's very complicated. But there is a new technique which starts in 1988, coming from logarithmic geometry of Fontaine, Ilusi, and then Kato, which allows not to do this. Well, my time is finished, but logarithmic geometry appears when you want to understand exactly how Milnor fibers decompose into pieces. So you start by playing a game with a concrete systems of equations. That game is combinatorial, tropical, and when you want to see how Milnor fibers decompose, there we apply logarithmic geometry, in a version adapted to such degenerations. I have to say the names. They are important. By first Kato Nakayama, and then this is 1999, and the way which it's really adapted to us, Nakayama August 2010. It's adapted globally, but we had to adapt it to singularities. As always, thank you very much for your attention.